Hello students, welcome to the next session of organic chemistry, that is hybridization of carbon. Now since we have gone through the basic characteristics of the sigma bond and the pi bond, we must be able to differentiate between the two easily. Now as we discussed earlier, sigma bond is formed by the axial overlap of two half-filled atomic orbitals, whereas in case of pi bond, the overlapping of the two half-filled orbitals is lateral or sideways in nature. The axial overlap in sigma bond is maximum, therefore the bond formed, that is the sigma bond, is strong in nature, whereas the overlapping is partial in pi bond, resulting in a weak pi bond. Now, electron density is concentrated around the sigma bond, that is along the line which connects the nuclei of the two overlapping atoms in sigma bond, whereas the electron density in pi bond is concentrated in two separate regions, as we saw in the diagram as well, which lie above and below the plane of the bonded atoms. The electron density is symmetrical for sigma bonds, whereas for pi bond it is unsymmetrical. Now, before we get into the details of hybridization, let's get familiar with two terms first, that is the sigma bond and pi bond. These are the types of covalent bond based on the linear combination of atomic orbitals theory. So let's start with sigma bond. The covalent bond which is formed by the overlapping of two half-filled atomic orbitals along their axis, that is, by end-to-end overlapping of the atomic orbitals, is known as sigma bond. In this type of axial overlap, the extent of overlap is maximum, and therefore the bond which is formed, that is the sigma bond, is strong in nature. The electron density of the orbitals is concentrated along the line which is joining the two bonded atoms. It is symmetrical about the line joining the two nuclei. Depending on the type of atomic orbitals that participate in their formation, the sigma bonds can be classified into three types. They are SS bond, SP bond, and PP bond. As is obvious from the name of the bond itself, the name is based on the type of orbital that participate in the formation of that type of sigma bond. For example, S orbitals participate in the formation of SS bond. S and P orbitals both participate in the formation of SP bond, and P orbitals participate in the formation of PP bonds. Now let's go through each type of these bonds one by one. So the first type is the SS sigma bond. In this type of bond, the S orbital of one atom overlaps with the S orbital of another atom to give rise to this SS sigma bond. Its example is hydrogen molecule, in which one S orbital of one hydrogen atom, which contains one electron, overlaps with one S orbital of another hydrogen atom, also containing one electron, to give rise to SS sigma bonds. The next type of sigma bond is the SP bond. As the name itself indicates, S orbital of one atom overlaps with P orbital of another atom to give rise to SP sigma bond. Its example is hydrogen fluoride, in which one S orbital of hydrogen atom with one electron overlaps with two P orbital of fluorine atom, which also has one electron. Please keep in mind that out of the three P orbitals, two will be completely filled, whereas one will be half filled in the outermost valence shell of fluorine atom. So that half-filled orbital will overlap with one S orbital of hydrogen atom to give rise to a sigma bond, which is SP in nature. The third type of sigma bond is the PP bond, in which P orbital of one atom overlaps with the P orbital of another atom to form a PP sigma bond. Example is chlorine molecule. Just like fluorine atom also has 5 electrons in its outermost P orbitals, that is of valence shell. So out of those three, two are completely filled with 2 electrons each, whereas the third one is half filled with 1 electron. That 3p orbital, which is half filled, will overlap with another half filled 3p orbital of another chlorine atom, and the two will give rise to a pp sigma bond. Another type of covalent bond is the pi bond. Please keep in mind that in sigma bond, the overlapping of the orbitals was axial, that is head-on. But in pi bond, the two half-filled orbitals overlap sideways to form this type of bond. This kind of sideways overlapping is less efficient as compared to the axial overlapping, and therefore the pi bond that is formed is weaker in comparison to the sigma bond. The electron density is unsymmetrical and is concentrated above and below the plane of the sigma bond. Two p orbitals form a pi bond. Example is ethylene, that is C2H4, in which this double bond is formed by one sigma bond and one pi bond. When we go through the hybridization in this molecule, we'll learn how exactly this bond is formed. Now, just to get an idea of how atomic orbitals overlap to give rise to a bond, let's take the example of oxygen molecule. We know that the oxygen molecule is formed by two atoms of oxygen. The electronic configuration of oxygen atom, as can be seen here, has two unpaired electrons. Its configuration is 1s2, 2s2, 2p4. Now, out of these three p orbitals, that is px, py, pz, any one of them will have two electrons and the rest will have one electron each. These two electrons may be present in px or py or pz, any of the three. But for the sake of convenience, we assume that two electrons are present in 2px and 2py and 2pz have one electron each. Now, out of these two half-filled atomic orbitals, one half-filled p orbital, let us say py, of an oxygen atom will overlap along the axis with another oxygen atom's half-filled p orbital. That can be any of the two. And they form a pp sigma bond. Now, the remaining half-filled orbital of that oxygen atom will overlap sideways with the other oxygen atom's remaining half-filled p orbital to form a pi bond. Thus, there are two bonds, one sigma and one pi, in the oxygen molecule. These two bonds together constitute a double bond. We can easily understand the formation of bonds in oxygen molecule with the help of this diagram. This blue orbital and this red orbital, these two are the half-filled atomic orbitals of an oxygen atom. These are the two half-filled orbitals of another oxygen atom. As they come closer, this blue orbital will overlap with this blue orbital, that is half-filled orbital of another oxygen atom, along the axis. So these two will overlap and form a sigma bond. As we discussed earlier, the electron density will be concentrated along the line joining the nuclei of the two atoms, that is in the middle, and it will be symmetrical in nature. Now, another p orbital, which is perpendicular to this blue orbital and is denoted by red, will approach another half-filled orbital of the other oxygen atom. This orbital is also denoted by red color for convenience. Now, as they approach closer, they overlap sideways. This lobe will overlap this lobe and this lobe will overlap this lobe. So together they will form a pi bond and the electron densities will be concentrated above and below the plane of the sigma bond. So this diagram shows a double bond between two oxygen atoms. I hope the fundamental characteristics of sigma bond and pi bond are clear to you, because we will be using these terms frequently in our next topic, that is hybridization. Hybridization can be defined as the mixing of two or more atomic orbitals which are present in the valence shell of an atom and possess different energies to form the same number of new orbitals of equivalent energy. These resultant orbitals are known as hybrid orbitals. The shapes and directional properties of these hybrid orbitals are different from those of the simple atomic orbitals from which they were formed. On the basis of the atomic orbitals, Participating in hybridization, we can classify hybridization into three major types, which is of interest to us as related to carbon atom. These are sp3 hybridization, sp2 hybridization, and sp hybridization. The first type of hybridization is the sp3 hybridization. As the name itself indicates, 1s and 3p orbitals participate in this type of hybridization. We are going to understand this type of hybridization with the help of methane, that is CH4. Now, we know that the electronic configuration of carbon atom in its ground state is 1s2, 2s2, and 2p2. Now, that means that any of these three 2p orbitals are going to have one electron each and one orbital will be left vacant. This orbital can be any of the three, px, py or pz, any of the three can be vacant. But for the sake of convenience, we will assume that px and py have one electron each and 2pz is vacant. Now that means that since carbon atom has two unpaired electrons, it must show a valency of 2, but we know that carbon is tetravalent. Now we can explain this tetravalency. As the two carbon atoms, which are to be covalently linked, approach each other, the potential energy of the system decreases and energy is released. This energy is utilized to unpair the paired up 2s electrons and then to promote one of them to the vacant 2pz orbital. Thus, the resulting electronic configuration of the carbon atom in its excited state is 1s2, 2s1, 2p3. Now each of the 2s and 2p orbitals has one unpaired electron. Now since there are four unpaired electrons present, carbon atom can form four covalent bonds by the overlap of each orbital with the 1s orbital of a hydrogen atom and form CH4 molecule, that is methane. But in that case, one of the four bonds will be different because one bond will be formed by 2s orbital and the rest of the three will be formed by 2p orbitals. But it has been found that in methane, all the four carbon-hydrogen bonds are identical and therefore the molecule is symmetrical. Now what actually happens is that these four half-filled orbitals of carbon atom combine and hybridize to form four identical sp3 hybrid orbitals. Now as can be seen in the diagram, these four sp3 hybrid orbitals are spatially oriented from the carbon nucleus towards the corners of a regular tetrahedron. The hybrid orbitals make an angle of roughly 109.5 degrees. The exact value is 109 degree 28 minutes. Now each of these hybrid orbitals will overlap with the 1s orbital of a hydrogen atom to form four sp3 sigma bonds. Thus we can see why methane molecule has a tetrahedral shape. All these four sigma bonds are identical in nature and the carbon-hydrogen bond length is around 0.109 nanometers. The second type of hybridization is the sp2 hybridization. As the name itself indicates, 1s and 2p orbitals participate in this type of hybridization. Its example is ethylene or C2H4. Now we have already understood how carbon acquires this electronic configuration in its excited state, which has four unpaired electrons in it. Now, during the formation of ethylene, 2s orbital of carbon combines with two half-filled orbitals, p orbitals I must say, let's say 2px and 2py, to form three identical sp2 hybrid orbitals, which are inclined at 120 degree to each other in the same plane. Now the unhybridized 2pz orbital remains perpendicular to the plane of the hybrid orbital. So two such carbon atoms then come together and one sp2 hybrid orbital of each of the carbon atom overlaps to form a sp2-sp2 sigma bond. And the remaining two sp2 orbitals on each carbon atom overlap with the 1s orbitals of four hydrogen atoms to form sigma bonds which are between carbon and hydrogen. Now the unhybridized 2pz orbital on each carbon atom will overlap sideways to form a pi bond. Thus, double bond is formed between the carbon atoms. One of these is sigma bond and the other is a pi bond. This ethylene molecule is planar in shape. It has 5 sigma bonds and 1 pi bond. The carbon-carbon bond length is 0.134 nanometer and the carbon-hydrogen bond length is 0.107 nanometer. The bond angle, of course, is 120 degree. This diagram will help us understanding the bonding between hybrid and unhybrid orbitals of the carbon atoms in ethylene. These red orbitals are the unhybridized 2p orbital, whereas 1, 2, 3, these three orbitals on each of the carbon atoms are the hybrid orbitals. These are at 120 degree with each other on the same plane, and the unhybrid orbital is at perpendicular angle to the plane of these hybrid orbitals. Now, as we can see, one of the three hybrid orbital will combine with one of the three hybrid orbital of the other carbon atom to form a sigma bond. These two orbitals will also form sigma bond with the s orbitals of hydrogen atoms. The same is true for these two orbitals, and this unhybridized orbital will overlap sideways with the unhybridized orbital of another carbon atom and form a pi bond. The other sp hybrid orbital of each carbon atom will now overlap with the 1s orbital of hydrogen atom that is also half filled to form two s-sp sigma bonds. So, carbon-carbon sigma bond was sp-sp bond and carbon-hydrogen sigma bond is s-sp bond. Now the unhybridized 2p orbitals on each carbon atom will now overlap sideways to form two pi bonds, which are at right angles to each other. Thus, the carbon-carbon bond is a triple bond, which contains one sigma bond and two pi bonds. Therefore, acetylene molecule is linear. There are total 3 sigma bonds and 2 pi bonds, and the bond angle is 180 degree. Now, as we can see in this diagram, these blue orbitals of each carbon atom are the sp hybrid orbitals, which will overlap axially to form sigma bond. Now these two are the unhybrid p orbitals which are perpendicular to each other. Both of them will overlap sideways. This is one pi bond formed by this orbital denoted in red, and similarly the other unhybrid orbital, which is denoted in green, also overlaps sideways, and these two pi bonds, one in red and other in green, are at 90 degree angle to each other. So now we can say that this acetylene molecule will have one sigma bond here between hydrogen and carbon, and one sigma bond between this carbon and carbon, and the third sigma bond between this carbon and this hydrogen atom. And there will be two pi bonds both between this carbon and this carbon. Our next topic is valence shell electron pair repulsion theory. This theory was proposed by two scientists, Sedgwick and Powell, and then it was later developed by R.J. Gillespie and Ronan S. Nilong in 1957 to its present form. This theory is used to predict the shapes and bond angles of polyatomic molecules. Now, according to this theory, the geometry of a molecule depends upon the number of valence shell electron pairs around its central atom. The electron pairs bonding as well as non-bonding, arrange themselves in such a way that there is a minimum repulsion between them. The molecule thus has minimum energy and maximum stability. Now, since there can only be one orientation of orbitals corresponding to a minimum energy, a molecule of a given substance has a definite geometry. In short, in this model, the valence shell electron pairs are arranged about each atom such that electron pairs are kept as far away from one another as possible, thereby minimizing electron pair repulsions. Now, when the central atom in a molecule is surrounded only by bonded electron pairs and not by lone pairs, the molecule has a regular geometry or shape, which depends on the number of bonded electron pairs. For example, boron trifluoride or methane. Now, when the central atom has both lone pairs and bond pairs, determining the molecular geometry becomes quite complicated. Three types of unequal repulsive forces are found in such molecules, which are the repulsive force between lone pair and lone pair, repulsion between lone pair and bond pair, and the repulsion between bond pair and bond pair. Now, as per the valence shell electron pair repulsion theory, the order of repulsive forces is lone pair, followed by lone pair, bond pair, and which is followed by bond pair repulsion. That means the repulsion between two lone pairs is maximum and repulsion between two bonded pair of electrons is minimum. Now, while electrons in a bond are held by the attractive forces exerted by two nuclei, the lone pair of electrons being associated with only one nucleus tend to occupy a greater angular volume and therefore cause higher repulsion. Now, let's discuss the molecular geometry of some of the examples that we are going to take on the basis of hybridization and valence shell electron pair repulsion theory. So our first such example is ammonia, whose molecular formula is NH3. In ammonia molecule, the central nitrogen atom is in the state of sp3 hybridization and contains 4 electron pairs. A regular tetrahedral configuration with bond angle 109 degree and 28 minutes is expected. However, the actual bond angle is only 107 degree. The distribution in ammonia molecule is explained by valence shell electron pair theory. In this case, one of the hybrid orbitals has a lone pair of electrons. Now, according to Westward theory, the force of repulsion between lone pair and bond pair is greater as compared to the repulsion between bond pair and bond pair. Therefore, it will result in the lone pair causing the 3 bond pairs to be pushed closer together, and thus the bond angle decreases from 109 degree 28 minutes to 107 degree. The shape of the molecule is thus pyramidal instead of tetrahedral, in which the nitrogen atom lies at the center of the molecule and the 3 hydrogen atoms form the base, while the lone pair forms the apex of the pyramid. Our next example is water molecule with the molecular formula H2O. Water molecule is also formed by sp3 hybridization. Oxygen atom in water molecule has 2 shared pair of electrons and 2 unshared pairs of electrons. Hence, the total number of electron pairs is 4. Therefore, oxygen atom is sp3 hybridized with expected tetrahedral geometry. But experiments have shown that the bond angle in water is not 109 degree 28 minutes. It is actually 104 degree 28 minutes, which can be rounded to 104.5 degrees. Now, this angle is smaller than the tetrahedral bond angle due to more repulsion of the unshared pairs of electrons than the shared pairs of electrons. Greater repulsion of these lone pairs compels the shared pair of electrons to squeeze closer together and thus decreasing the bond angle from near about 109.5 degree to around 104.5 degree. Our next example is hydrogen cyanide with the molecular formula HCN. Now, carbon atom in hydrogen cyanide forms a single bond with the hydrogen atom and triple bond with the nitrogen atom and has no unshared pair of electrons. Nitrogen atom forms a triple bond with carbon atom and has one unshared pair of electrons. Now, triple bond is counted as one shared electron pair. Therefore, carbon having two shared pairs of electron is sp hybridized. Nitrogen with one shared pair and one unshared pair of electrons is also sp hybridized. The geometry of the molecule is linear and the bond angle is 180 degrees. Next example is carbon dioxide. The molecular formula is CO2. Carbon atom in carbon dioxide forms two double bonds with two oxygen atoms, whereas each oxygen atom forms one double bond with the carbon atom and also has two unshared pairs of electrons. Now, since double and triple bonds are counted as one bonding pair of electron, therefore, carbon atom with two double bonds is counted to have two pairs of electrons and thus is sp hybridized. Each of the oxygen atom has three electron pairs, out of which two are unshared and one is shared. Therefore, it is sp2 hybridized. The geometry of carbon dioxide molecule, as can be seen, is linear and the bond angle is 180 degrees centigrade. From the above mentioned examples, we can conclude that the hybridization of a carbon, oxygen or nitrogen atom can be determined with the help of the number of pi bonds the atom forms. If it forms no pi bond, that is all are single bonds, it is in sp3 hybridized state. If it forms one pi bond, that is one double bond, it is sp2 hybridized. And if it forms two pi bonds, that is either one triple bond or two double bonds, it is sp hybridized. Our next topic is polar and non-polar bonds. So first of all, let's discuss the characteristics of a non-polar bond. When a covalent bond is formed between two atoms of the same element or between two atoms whose affinity for electrons, that is their electronegativity, is almost same, the pair of electrons will be shared equally between them. Such a bond is said to be a non-polar bond and the molecule is said to be a non-polar molecule. The example of molecules having this type of non-polar bond are hydrogen, chlorine, fluorine, nitrogen, and oxygen. Now in these examples, since the pair of electrons is shared equally between the two atoms, the bond formed will be non-polar. The bond opposite to the non-polar bond is the polar bond. When a covalent bond is formed between two different or unlike atoms, one having greater affinity for electrons than the other, that is, one atom is more electronegative than the other, the electron pair is not shared equally between the two. Instead, the more electronegative atom will have a greater share of that electron pair than the other. It will have a greater attraction towards the electron pair, so the electron pair will be shifted slightly towards that more electronegative atom. Such a bond is said to be polar bond and the molecule is said to be a polar molecule. The example is hydrogen chloride, water, ammonia, etc. A special type of bond is hydrogen bonds. Consider a molecule of the type HX in which hydrogen atom is linked to a strongly electronegative atom denoted by X, which can be fluorine, oxygen or nitrogen, and hydrogen and X are related to each other by a normal covalent bond. Now the electron pair is shared unequally, of course, because X is much more electronegative as compared to hydrogen. Hence, the shared pair of electrons will lie further from the hydrogen atom, so that the hydrogen atom will carry a partial positive charge. And since the electron pair will be more towards the X atom, X will carry a partial negative charge. In other words, the molecule HX becomes polar and behaves as a dipole. Now when another HX molecule comes close to this molecule, then there will be an electrostatic force of attraction between the positive end of one molecule and the negative end of the other molecule. The situation can be represented with the help of this diagram, in which these HX molecules act as dipoles. There is an electrostatic force of attraction between the negative end of one dipole and the positive end of another dipole, which is represented by hydrogen bond, shown with the help of these dotted lines. These dotted lines represent ordinary covalent bonds. Thus, we can define hydrogen bond as the attractive force which binds hydrogen atom of one molecule with electronegative atom, which may be fluorine, oxygen or nitrogen, of another molecule, generally of the same substance. Now, it may repeat several times, leading to the association of several molecules forming a cluster, such as water. It may even act as a bridge between two oxygen atoms, and is found in many compounds such as hydrogen fluoride, ammonia, etc. Now let's go through some of the general characteristics of hydrogen bonds. Hydrogen bond is purely electrostatic in nature, formed between the positive end of one molecule and negative end of another molecule. The molecules act as dipoles, and therefore hydrogen bond is a special case of dipole-dipole attraction. Hydrogen bond is very much weaker as compared to a covalent bond, and its bond energy ranges from 2 to 10 kilocalorie per mole or 8.4 to 42 kilojoules per mole. Hydrogen bond is longer than a covalent bond. Its formation does not involve sharing of electrons, therefore it is quite different from the covalent bond. Also, since it does not involve transfer of electrons, which is completely from one atom to another, therefore it is quite different from ionic bonds as well. Now, hydrogen bonds have been classified into two types. The first type is the intermolecular hydrogen bonding, and the second type is the intramolecular hydrogen bonding. Now let us see what is the basic difference between these two types. The first type of hydrogen bonding is the intermolecular hydrogen bonding. When hydrogen bonding takes place between various molecules of same or different compounds, it is termed as intermolecular hydrogen bonding. The association may involve large number of molecules, as in the case of hydrogen fluoride, water or alcohol, or only a limited number of molecules, as is the case with carboxylic acids. These are some of the examples of intermolecular hydrogen bonding, such as hydrogen fluoride, alcohol, and ammonia, in which a large number of molecules combine to form clusters, and also carboxylic acid, in which there is an association between only two molecules. As we discussed earlier, intermolecular hydrogen bonding is sometimes also observed between molecules of different compounds. For example, between ammonia and water, between alcohol and water, as can be observed in their solutions. This diagram shows intermolecular hydrogen bonding in para-nitrophenol. This is the reason why the para isomer of nitrophenol has higher melting point and low volatility as compared to ortho-nitrophenol, which shows intramolecular hydrogen bonding. The second type of hydrogen bonding is the intramolecular hydrogen bonding. This type of bonding arises due to the electrostatic force of attraction between hydrogen and an electronegative element present in the same molecule. This results in ring formation, also known as chelation. For intramolecular hydrogen bonding, there is a prerequisite that the molecule must be planar in geometry and must also contain two groups, such that one group contains hydrogen atom linked to a highly electronegative atom, and the other group contains an electronegative atom linked to a lesser electronegative atom. Intramolecular hydrogen bonding has been exhibited by orthonitrophenol and orthochlorophenol. The compounds which have intramolecular hydrogen bonding, that is the orthoisomers, have lower melting point than the other isomers such as meta or para isomers which exhibit intermolecular hydrogen bonding. We have already discussed the intermolecular hydrogen bonding in para isomer of nitrophenol, which shows higher melting point and lower volatility than this orthonitrophenol. Water exhibits certain unique properties due to the presence of hydrogen bonding in it. Let's discuss some of the properties. The first is abnormal boiling point. Due to hydrogen bonding, there is association of water molecules to form water molecule clusters. Energy is required to break this association and therefore the boiling point is abnormally high. Hydrogen bonding is also responsible for the existence of water as a liquid at ordinary temperature. Sulfur, which exists next to oxygen in its period, is supposed to show similarity with oxygen in its behavior, but hydrogen sulfide exists as a gas because there is no hydrogen bonding in it, whereas water exists as a liquid due to hydrogen bonding. Another property is that the density of solid water is less than that of liquid, while normally the density of a substance in the solid state is more than that in liquid state. The reason is that in ice, the hydrogen bonding between water molecules is more extensive than in liquid water. The molecule of water is rigidly fixed in ice, and the water molecules are tetrahedrally oriented with respect to one another. Each oxygen atom is tetrahedrally surrounded by 4 hydrogen atoms, 2 of which are bonded covalently, as shown by solid lines, and the other 2 are bonded by hydrogen bonds, shown by dotted lines. The hydrogen bonds are longer than covalent bonds. This arrangement gives rise to an open cage-like structure with a number of holes or open spaces. These vacant spaces are responsible for the lower density of ice. As ice melts, a large number of hydrogen bonds are broken. The water molecules move into the holes or open spaces and come closer to one another than they were in the solid state. This results in a sharp increase in the density. The density of liquid water is therefore higher than that of ice. Maximum density is displayed at 4 degrees centigrade. As liquid water is heated from 0 degrees centigrade to 4 degrees centigrade, the hydrogen bonds continue to break and the molecules come closer and closer together. This leads to contraction. However, there is also some expansion of water due to rise in temperature as in other liquids. It appears that up to 4 degrees centigrade, the former effect predominates and hence there is net contraction in volume or increase in density. Above 4 degrees centigrade, the normal expansion due to rise in temperature predominates, therefore increasing the volume or decreasing the pressure. Now let's have a look at some of the reasons why hydrogen bonding is considered important. First of all, without hydrogen bonding, water would have existed as a gas like hydrogen sulfide, and no life would have been possible on this planet, that is Earth. Second, hydrogen bonds are important in biological systems. It exists in various tissues, organs, blood, skin, and bone in animal life. The structure and properties of proteins also depend on the existence of hydrogen bonds. Hydrogen bonding plays an important role in making wood fibers more rigid and thereby increasing their utility as an article of housing, furniture, etc. Cotton, silk, or synthetic fibers owe their rigidity and tensile strength to hydrogen bonding. The stickiness of glue or honey is also due to hydrogen bonding. There are quite a few examples given on this topic in our online course, so I suggest that you refer that and solve as many examples as possible to get a grip on this topic. But in this session also we are going to solve a couple of examples. The first one is hybridization of carbon atoms in carbon-carbon single bond of this compound is choice A, sp3sp3, choice B, sp2sp3, choice C, sp2sp2, and choice D, sp2sp. Now this is the carbon-carbon single bond. So first of all, see what is the hybridization of this carbon. We discussed in this chapter that one triple bond is equivalent to one pair of electrons. Another bond is also equal to one pair of electrons. So since it has two pair of electrons, we can say it is sp hybridized. This is also equivalent to the carbon in acetylene. So we know this is sp hybridized. The second carbon atom, it forms one double bond that is equivalent to one electron pair. Second bond with hydrogen, so the total becomes 2 electron pairs, and third bond with this carbon atom, so the total is now 3 electron pairs. So it should be sp2 hybridized. So our answer is sp2 hybridized. So our answer matches the last choice, so it will be D, that is sp2sp. Next example. In the given compound, what is the type of hybridization of C2-C3 bond? Numbering starts from the left. So C1, C2, this is C2 and this is C3. We have to find the hybridization of these two carbons so we can tell what kind of bond it is. Now let's see what is the hybridization of C2 carbon, that is this one. It forms a double bond equivalent to one electron pair, one bond with hydrogen equivalent to second pair of electrons, and one bond with carbon atom, so total 3 pairs of electrons. So it should be in sp2 hybridized state. This is our C3 carbon. It forms 2 bonds with the carbon atoms and 2 bonds with hydrogen atoms, that is total 4 bonds. So it should be in sp3 hybridized state. So our answer is sp2 sp3, which matches the last choice, that is D. Next example. Which of the following compounds represents the mode of hybridization? sp2, sp2, sp, sp from left to right. So let's check the first example. This carbon atom forms 2 bonds with hydrogen atom and 1 bond with another carbon atom, that is 3 bonds equivalent to 3 electron pairs on it. So it is sp2 hybridized. Second carbon also forms one double bond equivalent to 1 electron pair and 1 bond with carbon equivalent to second electron pair and 1 bond with hydrogen equivalent to third electron pair. So it is sp2 hybridized. Third carbon forms 1 bond with carbon equivalent to 1 pair and a triple bond with nitrogen equivalent to second pair. So it should also be sp hybridized. The last atom is nitrogen, which forms 1 triple bond equivalent to 1 electron pair. But we must not forget a lone pair of electrons present on nitrogen representing the second electron pair. So it is also sp hybridized. So the correct answer to this question is choice